Hello, I'm a faculty member at Texas A&M. My name is Linda Katehi, and I'm delighted to be able to make a presentation during your conference. What I would like to speak today from the many topics that I was given the liberty to select from is to talk about an issue that is very dear to my heart. Is a research issue. And I would like to then talk about my research for the last few years. It took me a lot longer to be able to move into this new research area. So what I would like to do is to share my screen, first of all, and I will also take this to view mode. So the topic of my presentation is embodied intelligence in electronics. And I would like to present this as a new path into high frequency circuit design, which I consider will define the types of circuits we are designing today for applications of tomorrow. So for those of you who have probably learned more about the spectrum and its usage, there have been a lot of projections about what, how big the usage of spectrum is going to be. But one by Cisco has projected that by 2023, which is just in a couple of years from now, we are going to have close to 24 billion users, wireless users, which of course will occupy a big part of the spectrum. And those users are not necessarily people. The majority of those users will be machines. So we're talking about a present and a future where the spectrum will be occupied by machines which are trying to communicate and communicate data of all types, from entertainment data to scientific data, of course. So here it shows, in fact, what the spectrum is occupied by, of course, all of the satellites around the Earth. And on the left, and here, in fact, this number grows substantially, but grows by leaps and bounds, as we say. And then, of course, you can see that we have a host of, going back, we have a host of users in our space. And then, of course, we have a host of users. And then this is a scenario which includes also defense on the on Earth's surface. And we have a host of passive users which are looking into deep space. So for all of these users will have a need to access the spectrum, and in fact, to access it with quality. So to be able to have the ability for machines to communicate in real time and to communicate effectively, we are talking about the need to allocate spectrum dynamically. And to be able to do that, to not to allocate, you have, of course, to be able to classify, to identify what is going on in your own vicinity. And then from there, to make decisions about which bands to use, what kind of modulations to use, what kind of other users to approach, and so forth. And that needs to happen in real time. So we are talking about intelligent systems that have the capability not just to acknowledge and classify what is happening in their own spectrum space, but also to be able to make the appropriate adaptations and use the space effectively, that space effectively. So we are talking about circuitry that is going to have the capabilities of artificial intelligence. Now, artificial intelligence is a discipline that has really seen and is seeing tremendous activity, from mathematics to computer science to engineering to data science and the whole thing. I mean, it's really now being used in almost everything, and the use of some form of a machine learning algorithm somewhere in the systems we're going to use in the future is going to be a certainty at this moment. So before I speak about how we use intelligence within electronics, I wanted to define intelligence. And I wanted to say that it is interesting that after almost in the last 2,000 years, if not longer, 2,500 years, we moved from one theory of intelligence to another and then back to the first one. So in the ancient years, in ancient Greece, Aristotle was considered to be the one who defined intelligence. And of course, not intelligence, but knowledge. According to Aristotle, knowledge depends on an inductive inference, which implies that you make a lot of observations as you interact with your environment. You use your sensory experiences, and on the basis of that, your mind can start thinking and have thoughts and emotions in ways that other species have not been able to master at this point. Now, later, many centuries later, and under the influence of the religious influence, I would say, in Europe, people reconsidered the primary role of the brain in a human's ability to interact and think. And according to Descartes, therefore, knowledge was only derived through reason from innate ideas, and it came from the brain. Nothing else impacted it. That was the Cartesian intelligence was what has really, for many centuries, guided our scientific observations, especially as it happens in psychology and neurobiology and so forth. It is only very recently that we have reconsidered how the brain works and how we become intelligent, how we can think and make decisions independently. And I think at this point we have embraced again Aristotle's definition of intelligence and knowledge. Now, what really helped in that transition from the Cartesian philosophy to the Aristotelian, it was our ability to make observations of how intelligence develops and how it is expressed in other species. One of those species that we have studied extensively is the cephalopods, and one particular species is the octopus. What we have really found there is that the brain is organized differently from the human brain, but these animals do have expressed capabilities, cognitive capabilities that we can identify today in children up to age 5. So they have the ability to make decisions and then to make either local decisions locally or to make decisions that involve movements from all the body. There is a difference also in the definitions of cognition and intelligence, and I would like to speak about those definitions so we know how to use the words right. Cognition is the process of learning. Intelligence is the manifestation of that. One is a process, the other is the result. And a lot of times when we speak about intelligence, we really imply, especially in electronics, as you will see later, we imply the development of electronic components that do not necessarily have the capability to make a decision. They have only the capability to adapt. But this is not the definition of intelligence. So A lot of you may have heard about cognitive radio. So again, we use the word cognition as opposed to intelligence. Sometimes people call it the intelligent radio or the software-defined radio, which is a more appropriate definition of what this radio is doing. So what is this really radio? It's a receiver, which of course incorporates an antenna and the front end of this. And then after an analog to digital converter, this all goes into a microchip where all of the processing happens in digital form. And of course, there are in there some feedback mechanisms which also control the frequency of the oscillator in some distinct, discrete ways. And then some limited also capabilities for control due to the programming in this structure. Now, this is an adaptable system, but it's not an intelligent system. And why is that? Because as we discussed previously, intelligent systems have the capability to make decisions on their own. Now, why is it that any of these systems that we have developed, no matter what we do at the back end, which is after the analog to digital converter, why is it that they can never become truly intelligent? The reason for that is because in a system, the TRX module, which is the transceive receive, is a deterministic engine. What that implies when I say deterministic, what I imply is that before we design this receiver or transmitter or transmit to receive, we already think of what kind of situations we want to solve. We then find the solution to these situations, and then we develop a design that is going to give us a response to these particular situations with almost 0% error. Now, these are deterministic systems. The good thing about deterministic systems is that for the solutions, for the situations, for the scenarios that they have been designed, they operate well. But outside of that space, which is also discrete, not continuous, they fail. What do we need to do to be able to change a deterministic system, a receiver, for example, to one that can be truly intelligent is that we have to replace the deterministic engine, which I show here, with a stochastic engine, which I saw there. But that implies that we are going to replace all of this that makes the receiver deterministic with only one engine, which will allow us to observe, incorporate that observations in the circuit operation, and then allow the circuit to learn and then make independent decisions, unsupervised decisions. How do we do that? That shows one effort that we have underway. And in fact, what we've done, we created a new synthetic filter mixer, which in fact has been realized by a memoristor crossbar configuration. And of course, it has around circuitry. And this configuration could have either the capability of operating in a space, but without constraints, learning from that space, and eventually making other decisions. So in the case of a synthetic filter mixer, the space can be a very broad band from 0 to 20, 40 gigahertz. And then in there, you can decide to use a filter of any type, a mixer for any frequency, and eventually bring a high frequency signal to the baseband. But that's where not that stops. After you bring your signal to baseband, then you feed it into a CNN or RNN network, an encoder decoder, and in between there you can have another layer or layers if it's a CNN network, or you can have only one layer if you use the Kuhlmann operator to represent this nonlinear system, because the receiver by itself, including everything, is nonlinear. And with that, what we have been able to develop at this moment is part of the system, which we are going to show you here. This is what we call the pre-processing, but it's done stochastically. So we have a crossbar filter with memory stores. Memory stores are resistive devices which can be controlled and also store information up to 11 bits. And then the incoming signal in the time domain is sampled. For this particular case, we went up to 20 gigahertz. So we sampled it at 40 gigahertz to satisfy the Nyquist theorem. And then from there, we developed with this single crossbar array, a filter, and then we did a down conversion. In fact, the filter is just a Fourier transformation that is happening through the crossbar configuration. What is the advantage of this? And then, of course, you go to the IDFT if you want to bring the signal in the time domain, or you just send out the signal in the frequency domain only if you want to use separately if you want to use only the baseband signal. But here you can see, in fact, how you can take a signal that is a PAM4, has been modulated, and then going through this crossbar configuration, you can demodulate the signal and find the symbol, but also you can see the constellation of I and Q. And that is without any local oscillator, but only with a crossbar configuration with memory stores. And in fact, all of these calculations, you can think the crossbar configuration is nothing else but a set of crossbars where your input signal comes as a voltage. Your memory stores are, as you will see here, your memory stores are connected through a CMOS to the ground, to the lower bar. So it's a shunt configuration between the bars. And in fact, by use of Ohm's law and Kirchhoff's law, you in a crossbar configuration like that, you are able to achieve multiplications and summations in one time step. And that time step is defined for how long it takes for an electron to go from an input bar to the output bar, which is a very short period of time, obviously, because the size of these memory step crossbars is very small. So a whole structure like this with about 256 crossbars can be at maximum 1 millimeter. So I know that my presentation is short. I wanted to say, therefore, that what we are trying to do right now is, and we are in the process of developing that, is not only to implement BRF tuner using this deterministic structure, but also to embed in there algorithms, which will help this structure take the baseband signals and analyze them using some deep machine learning algorithm, and then provide classification for this signal. Now, either that's going to be your output, depending on what you're looking for in your spectrum, or it could be information that goes there into another chip, go through an A-to-D converter, but the information is going to be much smaller in volume than what you produce by sampling the signal in time. And of course, it can be stored in a long-term memory or can be utilized for higher level decision making. So with that, I wanted to just show what our work entails. If we want to create a stochastic engine, as we have discussed, I'm trying to move my, this is what we call a PMAA, which is like a programmable memory store adaptable array. And it of course incorporates hardware, incorporates software which is embedded in the hardware, and of course we need training and testing data sets to be able to train the algorithms. So with that, I would like to end my presentation and thank you. You may have a number of questions, but I would be very pleased to respond to your questions if you can email me. And the email is katehi, Katehi, at tamu.edu. Thank you so much.